Structure won't be the same if there are two edges between the same two set of vertices, right? In that case, it won't be the same.
I'm sorry?
If there are two edges, if there are multiple edges between the same two vertices, that case I think it's
multiple edges between the same set of vertices.
then you need to account for the degrees. Because in the adjacency matrix, you'll still have just technically one there.
I'm not sure I follow what you said.
So in the adjacency matrix, if there are multiple edges between the same two vertices,
Yes.
so it will still be just one in the adjacency matrix.
Correct.
But when you take the degrees, then you need to, then that will be considered by degrees now.
True, but suppose I have a simple graph where I don't have multiple edges between the same pair of vertices.
The adjacency matrix to have two instead of one if there are two edges. But then that's not the definition. That's the matrix. But then also if I take x transform AX, considering that amendment, won't it be the same? That will be the multiple minimizer.
Yeah, let me think about it and get back to you by the next class. All right, so let's start. So in the last class, we saw what a convex function was. A convex function in one variable was, and we're trying to understand both the geometric and the analytic properties of these convex functions. So basically we want to answer the question, what kind of functions are easy to minimize, right? Both with constraints and without constraints. So for now, I gave this general definition of a convex function. That is, the function f is convex if you take any 2 points, then the straight line joining these 2 points basically lies above the curve. Right, that's the geometric interpretation, and here's the analytic definition of a convex function. And we saw that a function is, we have a necessary and sufficient condition for a sufficiently smooth function to be convex, and that is if the second derivative exists at all points, then it's convex if and only if the second derivative is always non-negative. Right, so this gives a simple test to check whether a given function is convex or not. Right, so to prove this, so in the last class we were trying to prove this particular statement, right? So the second derivative must be non-negative for a function to be convex, and we proved one way. So what we showed in the last class was, suppose that the second derivative is always non-negative, then it is convex. Correct? Any questions with that proof or any other topic that we discussed last time? Any questions? Okay, so then let's try to prove the other way around. That is, if a function is convex, then the second derivative must always be non-negative, right? So the reverse implication. So what do we want to do? We want to show that if f is convex and the second derivative exists at all points, then it must necessarily be non-negative. Right? And this is fairly easy to prove. Right, so what is f double prime of x equal to? Yeah, do you remember it from your high school calculus? Okay, we're evaluating it at x, right? So let's take a limit t tending to 0 of
f dash of x plus t.
Okay. Dash of x plus t
Minus f dash of
okay, divided by t. Right, but what is this quantity equal to? This is f of x plus t minus, okay, so maybe I should write it in a slightly different way. Fine. Oh. I can write it. Minus do you agree? Right? So let's just simplify this. So this is just limit t tending to 0 of f of x plus t. I have a minus f of x minus f of x, so it's minus 2 times f of x, and a plus f of x minus t. Whole divided by t square. Right? So if I'm able to show that this quantity is always greater than or equal to 0 for all t greater than 0, so maybe I should have been a little more precise when I wrote this. So here I'm assuming that t is always positive, so t is tending to 0 from above. Right? So now, if I'm able to show that this numerator, so t square is always non-negative, but I'm not really sure if f of x plus t plus f of x minus t minus 2 times f of x is always greater than or equal to 0 or not. Okay? So let us look at that particular quantity. So f of x plus t plus f of x minus t minus 2 times f of x. Correct? I'll write this as 2 times f of x plus t by 2 plus f of x minus t by 2 minus f of x. Okay, I'm just nothing but rearrange the terms of it. Okay, now what do we know about the function f? It's convex, right? So can we use this property here? How? Okay, so let's take alpha equal to half, x1 to be x plus t, and x2 to be x minus t, right? So then what do we get? What does inequality say?
F of alpha x1 plus alpha 1 minus alpha x2 is equal to alpha by 4x1 plus 1 minus alpha.
Okay, so this basically, this is greater than or equal to this term on its own, f of x plus t by 2. So half times f of x plus t plus half times f of x minus t, which is alpha times f of x plus t plus 1 minus alpha times f of x minus t. This is greater than or equal to f of x plus t by 2 plus x minus t by 2. Right? So this quantity is greater than or equal to this particular quantity. Right? But what is this quantity equal to? This is just f of x. So that you have f of x minus f of x, which is greater than or equal to 0. Right? That's straightforward. Correct. So therefore, we now have a necessary and sufficient condition for a function of real variable to be convex. right? So we're only looking at f from R to R. We've not generalized it to higher dimensions yet. And as we'll see, things become a little more nuanced in that case. Okay, but the basic interpretation, the basic geometric idea still remains the same, right? So that is why we want to build up. We want to see R1 so that we can visualize functions in R. We can maybe visualize functions over R2, but beyond that, our visual interpretation does not necessarily help. Things can go wrong in higher dimensions. So we want to just build not just intuition, but also the formalism that is required to generalize this to higher dimensions, right? So, in fact, there are a couple of points that when we define a general notion of a convex set, a general optimization problem, there were some things that are still sort of left open, and we'll take care of some of those in this particular class. Right? So, any questions so far? Okay. So, before we move on, let's see some examples of functions which are convex and some which are not. So, can you give me an example of a convex function, not a polynomial, perhaps something else? Okay, x log x. So, maybe before that, what about f of x equal to log x? It's concave, right? It looks something like this visually, but you can evaluate the first derivative and the second derivative, and you see that it's always less than 0, right? So this is concave. Sorry, e to the power minus x. This is it convex or concave? Convex. Everyone agrees that this is convex. Right, let's go back to that example. So f of x equal to x log x. Yeah, it's convex. Okay, if you are in doubt, then what is f dash of x equal to? Let's assume that the base is e. Yeah, not convex. So what is f dash of x? It is 1 plus log x. What is the second derivative? 1 by x. So for x, again, you have to define over what is the domain in this case. So let's suppose that it is the set of all non-negative positive numbers, right? So it is convex, because otherwise it's not even defined, right? So you have to take the set of positive real numbers. So this is greater than 0 for x greater than 0, so it's convex. Okay, let's look at another example. So f of x equal to x log x plus 1 minus x log 1 minus x for x between 0 and 1. Check. Is it? Okay, it's x log x, yeah. So this is convex. If I take a negative, then it's so this is convex. What about f of x equal to 1 minus x log 1 minus x for x between 0 and 1? Yeah, it's convex. Okay, any other examples? It's convex. But how do you verify that this is convex? Yeah?
It's not.
No, you can't differentiate it, yeah. The derivative does not exist at x equal to 0. So how do you prove that this is convex? You can draw the curve and see that it is convex, I agree. But that's what. We want to go beyond just visualizing, right? Because if I want to see things in higher dimensions, then this doesn't help. So I need to be able to prove things.
If the limits from both sides, then each of the limits is convex
Limits on both sides.
of 0.
That can go horribly wrong. So let's take f of x to be equal to, let's say, x for x greater than or equal to 0. And let us say it is, no, not minus x. So minus x plus 1 for x less than 0. You can take the second derivative, first derivative, and see that both the second derivative and the first derivative is equal to this function, right? But what does the function look like? It looks like this, right? Is this convex? This function is convex because I can take these 2 points, this point, and I have the straight line joining these 2 points below. Okay, so now how do I prove that mod x is convex?
When x is both the x we are taking out both same side of 0 and
Okay.
when they are different sides.
Okay.
Yeah, so when they are same side, we can prove that it would be equal.
Okay.
Not work out for different sides. So I
Okay.
think it should work out.
You think, right? We still want to show, yeah.
We can just use like the definition of like convexity,
Correct.
and we can use the properties of mod. Like we can just take alpha x1 plus 1 minus alpha x2, then be less than or equal to alpha of mod x1 plus 1 minus alpha mod x2.
Exactly.
So from there, take that.
Yeah. So you just take, let's use the definition. So pick any x1 comma x2. Maybe if you want, we can just take what x1 less than x2. So let's look at f of alpha x1 plus 1 minus alpha x2, right? So this is mod alpha x1 plus 1 minus alpha x2. What do you know about the mod? What is mod y1 plus y2 compared to mod y1 plus mod y2? This is less than or equal to mod alpha x1 plus mod 1 minus alpha x2, which is equal to alpha mod x1 plus 1 minus alpha mod x2 1 minus alpha f of x2, right? So depending on the function you have, you might need to use a different property. So the second derivative test is extremely helpful, but at times it's easier to just use the basic definition, right? All right. So any questions so far? Okay, so right now maybe we'll switch topics a little bit. Maybe before that, so we know what a convex function is. What other properties make the convex function nice? How many minima can a convex function have? One. Why?
Just for anytime that it goes for the maxima side, if the function has some maxima as well,
Okay.
then that part will always be concave.
Why?
So you just still we are x1 and x2 below 2 points of minimum.
Join that line.
Yeah, correct. So suppose there are multiple points of minima, then you can just draw a straight line between those two minima. There should be, again, you have to be a little careful over here, because I can construct a function which has multiple minima, right? In particular, yeah, something like this, right? So it doesn't necessarily have to be continuous. It doesn't have to be differentiable. Convex function, you can have multiple minima.
In general,
In general, well, this is in general, right? In general, you can have multiple points of minima. Yeah,
with multiple minima.
The value of the
Why not?
function would-
correct. The value of the function would still be the same. In particular, there can be only one minimum value. You cannot have multiple local minima, right? Okay. And why can't it have a maximum?
But it doesn't depend on the range we are defining, right? Like if it,
Okay,
so if we take the range over all of
Correct.
R,
correct.
then if it has a maxima, it implies that the curve comes down after that.
Yes,
So
correct. So that's why it's nice. I mean, things become much better if you have a smooth function, right? If you have a smooth function, then you can prove all of these things much more easily. In particular, how many stationary points can a smooth, so suppose you have a function for which the second derivative always exists, right? In this case, how many stationary points can exist? Yeah, you can have infinitely many stationary points, right? Because I can just take f of x equal to 1 for all x, right? So every point is a point of minimum in this particular. But as we said, this in many cases we don't have such extreme functions, but nevertheless, suppose that there exists one stationary point, right? So I'll take an f of x for which I have one stationary point, f of x, and I evaluate, let us say, I find x such that f dash of x is equal to 0. What guarantees can I give about this particular point? Suppose that the first derivative always exists, and the first derivative is equal to 0 at some point. Then it's a convex function. Yes, f is a convex function.
and only one point is
I can have multiple points, but okay, let's assume that there's only one point for which the first derivative is equal to 0.
Like the value of x and this x is the minimum.
Okay, and why is that? Suppose that the first and the second derivative all exist. Okay, both the first and the second derivatives of this function exist. F is convex, and I am telling you that there's only one point for which the first derivative is equal to 0. Yeah, it's a stationary point, sure. And the claim is that this is a point of minimum. Why is this a point of minimum?
The double derivative is always straight across.
Okay, so
So it's always like
Yeah,
After that, the slope of the slope will increase.
correct.
maximum distance.
Correct. So for all, let me call this x star. Okay. So I know that for all x which is less than x star, the slope is less than this. Right? Right? Since the slope is less than this, it means that for, and at this point it's equal to 0, which must mean that for all x less than or equal to x star, f of x should be a non-increasing function. So I take x, this is the value, this is my x star. So for all x less than x star, it's a non-increasing function. It could be flat for all I know, but it's definitely non-increasing. Okay. What about, so what this means is that f of x should be, for all x less than x star, what can you say about f of x? Should be greater than or equal to f of x star. Right? Because x is decreasing, non-increasing certainly. Okay, so now let me take x greater than x star. What can you say about the derivative? This is greater than or equal to f of x star. Right? So beyond x star, it's an increasing function. It's always increasing. It can never decrease beyond that point. So what can you say about f of x? It's always greater than or equal to f of x star. Therefore, this should be a point of minimum. It may not necessarily be the unique point of minimum, but it is certainly a point of minimum.
So the curve is smooth.
Because I'm saying that f, both the first and second derivatives exist. But that's the only guarantee that I'm giving you. Correct? Yeah. So it may seem that I'm making things too formal, but we'll see that this is important as we go along. If you want to really generalize, if you want to solve more complicated problems, then we need a certain level of formalism. Any questions? Okay. So now we'll take a slight detour. And here are some wise words. You don't understand things, you get used to them. So we'll, in this class, we'll define a number of new things. You may have seen some of these things before, but some of them you may have not seen these concepts in such a level of formalism. But it's not too complicated. There is a lot of intuition behind this. But at the same time, it's a matter of getting used to the terms, getting used to the concepts themselves, right? As you get used to them, you'll get comfortable with it. Okay? So again, these are all elements which come from basic calculus, right? So we're going to go back to high school and then try to revisit some of these things, but we're going to do it a lot more formally, more carefully this time. Okay? Okay. So we'll start with subsets of real numbers, right? We're going to go into set theory. What is an open set? What is a closed set? You've all seen closed sets, open sets in terms of intervals over subsets of the reals. All right. But if we really want to generalize it to more complicated problems, we have to really understand what kind of sets are we going to optimize over, right? What kind of functions? What are the properties of the functions? What does it mean for a function to be convex? For sets to be closed or bounded or compact or whatever it is, right? So, okay. So now suppose that I am giving you an arbitrary set, okay, of the real numbers. Let's call it A, right? So this is some subset of the real numbers, the supremum of A. So we'll define a notion of a general upper bound, right? It's a set of numbers. So an upper bound is any number for which that number is greater than every number in this set, right? So we say that, say U is an upper bound for A if U is greater than or equal to X for all X in A. Straightforward, right? But I'll also introduce the notion of a least upper bound, right? So a least upper bound, which is also called a supremum. So we say that U star is the supremum, also denoted sup, of A if the following holds. So firstly, U star should be an upper bound for A and secondly, it's the smallest possible upper bound for A. So if U is any other upper bound, then U star is less than or equal to U. If U star, which is the supremum of A, if this is also in the set A, then we say that U star is a maximum of A. So in this case, the maximum exists. Okay, so let's see some examples. So suppose I have the interval 0 to 1. In this case, what is the supremum? Yeah, straightforward. Equal to 1. Does it have a maximum? No, right? So, and how do you verify that this is indeed the supremum? So firstly, the first property is clear, right? So U star is an upper bound because for every, the way I've defined A is, this is just the set of all real numbers X, which is strictly greater than 0 and strictly less than 1, right? So just by this, X is always going to be less than 1, but it's also an upper bound, the smallest upper bound. Yeah.
Is smaller than 1. And then
Correct.
say that there exists a number in A which is greater than that.
Okay, very good. So so basically you take any y which is strictly less than 1. Right? Then again, by definition, this belongs to the set A. So therefore it cannot be an upper bound for A. So therefore A must be the smallest upper bound for A. Sorry? You have to show that there exists at least one element.
Greater than
Correct. Okay. Yeah. So you take, so y is strictly less than 1. Right. So what can you say about 1 minus y? This is,
limit y in the left hand side also if it's greater than 0.
what do you mean y in the left hand side?
I mean, do we also take y to be greater than 0? This.
Not necessarily. I don't really, not yet at least. Right. So again, what we want to show is that if I take any number which is less than supremum of A, then there is at least one point in A which is larger than that particular. Basically, it's not an upper bound for A. Right? So suppose I take 1 minus y. Okay, I know that this is greater than 0, correct, by definition. Let me call this some epsilon. What can I say about y plus epsilon by 2? So let's think about it geometrically. This is 1. I'm taking some y which is less than 1. Maybe it is some point here. What I want to show is that this cannot be an upper bound for this set, right? The set is 0 to 1. If I take any point y which is less than 1, I should be able to find a point to the right which lies in the set A, and therefore y is not an upper bound. So let me take y plus, so this distance over here is epsilon, right? What about y plus epsilon by 2? This is greater than y, and it is less than 1. Therefore, this point is in the set A. Correct? And therefore, this cannot be an upper bound. Questions? Okay. So similarly, just as we defined an upper bound and a least upper bound, or a supremum, you can also define a lower bound and the greatest lower bound. Right, so I say that L is a lower bound for A. If L is less than or equal to X for all X in A. And similarly, L is the least upper, the greatest lower bound for an infimum if so firstly L is a lower bound for A, so let me say L star, and if L is any other lower bound for A, then L is less than or equal to L star. If L star is in the set, then L star is the minimum. So here's a general question. We're generally looking at subsets of R, right? Suppose instead that I look at subsets of the integers or maybe subsets of the rational numbers. Is it true that a greatest lower bound or the infimum and the supremum should always exist? Okay, someone who says no. So firstly, if I take any subset of the reals, okay, take any subset, does the supremum and infimum always exist for this subset? No? Can you give an example of a subset which does not have a supremum? Sorry?
X greater than 0.
X greater than 0. Okay, so in this case, it does not have a supremum. But for example, if I extend the reals by including plus infinity and minus infinity, then I say that infinity is an upper bound for this particular set. But in fact, infinity is not a real number, right? So if it does not have an upper bound, a supremum in the set of reals, then I say that plus infinity is the supremum. Similarly, if I take a subset of reals and it does not have an infimum, then I say that minus infinity is the infimum. Okay. Now, if I take an arbitrary set of rational numbers, does it always have a supremum? A bounded set of rational numbers, does it always necessarily have a supremum? Okay, some people saying no. Why? Okay, very good. So you take the set of all rational numbers. So my space is the set of all rational numbers at this point. You take this particular set. So take A, subset of the rational numbers, and A is defined as the set of all rational numbers x such that x square is less than 2. Right? If I viewed these as a subset of let's say real numbers, then what does this have? An infimum, sorry, a supremum? Yeah, it is root 2, correct? So in the set of real numbers, the supremum of A is root 2. Does everyone agree with this? Any questions here? Okay, but now if my space is the set of all rational numbers, then what is the supremum of A? Yes? Yeah, so this is an example of a set which does not have a supremum. So that's one reason why we always focus on the set of real numbers or the set of complex numbers. In a sense, they're what are called complete sets. So in this case, this does not exist. Right? So now we've seen cases where the maximum does not exist. So this was an example of a case where the maximum does not exist, but the supremum exists. This is an example of a case where even the supremum does not exist, but that's because we focused on a different set, the set of rational numbers. Correct? Okay. So in general, if you're looking at functions of real numbers, then there is at least a well-defined supremum and an infimum, but the maximum and minimum may not exist, right? So that's something we need to be careful about. When we're optimizing, what we want to ensure is that a maximum exists. If you're trying to minimize a function, then we want to ensure that the minimum exists, right? That is the basic guarantee that we want to give, and only then we're going to design algorithms to achieve or find this minimum, right? So what is that class of functions for which the minimum exists, right? That's a lot of question that we're going to try to answer today. Okay, so first, let's look at functions. Let's just get some definitions sorted out. So I have a function from one set to one other, right? So this is some set X, this is some set Y. F is basically a mapping from this set to the set Y. The set X is called the domain, and the set Y is called the codomain. Right? Now the function f need not take x and map it to all of y. Right? For example, if I take f of x equal to x square, f from R to R, then not every y has a corresponding x. Right? So negative numbers don't have a corresponding x. Right? So in that case, f maps x to some subset of y. Right? And what is this set called? The range. Right? And I'll sometimes refer to the range as f of this set x. Right? So by this I mean the set of all y for which, or in other words, the set of all f of x. Similarly, if I take any subset of x, right, take any, let's say A, which is a subset of the domain, then f of A, which I say is the set of all values of f of x, for which x is in A. So this is what I call the image of A. Right, so basically I take a subset. This maps to some subset of the range. And that is what I call the image of A. For example, if I take again f of x equal to x square, and maybe I want to know what is the image of the interval 2 to 3. Right? F of x equal to x square, image of 2 to 3, what is it equal to? 4 to 9. The interval from 4 to 9. Okay, and similarly I define for a set on the left, I can find the corresponding set on the right, that is the set of all points which this set gets mapped to. Now similarly I can try to look the other way around. Given a subset on the right, I want to know what its inverse image is. So I take some B, subset of Y, I say f inverse of y is the set of all x such that f of x, maybe say f inverse of b, f of x is equal to, or f of x is in the set B. This is what I call the inverse image of B. Okay, again, you may have seen all of these things before, but based on the inverse image. So remember that the inverse image of a particular set, it could potentially even be an empty set, right? For example, if I take f of x equal to x square, what is the inverse image of minus the interval from -1 to -2? That's an empty set. Right? So based on the size of the inverse image, sometimes called the pre-image, you can classify functions in various forms. So a one-to-one function is one for which the inverse image of every point on the right is either has size 1 or size 0. Right? So for every point on the right, exactly one point, you can find exactly one point on the left, or you can find no point on the left. Right? It is onto or surjective if is equal to, so the codomain is basically equal to the range, and it's bijective if it is both. Right? Again, basics, you've seen this before, but just to refresh things. All right, any questions? Okay. Right. So now, given a particular set, we also want to understand how big this particular set is. Right? So if a set has finitely many elements, it's finite, and if not, it is infinite. But even infinity can come in different forms, right? So a set can be finite or infinite, and in particular it can be either countably infinite or uncountably infinite. Have you seen this notion of countable infinity and uncountable infinity before? Is there anyone who has not seen countable infinity and uncountable infinity before? It's okay if you've not seen it before. So, okay, so when do you say that a set is countably infinite? Or when do you say that a set is countable?
Index with index.
Okay, so basically, fine, you can say that a set is countable if there exists a bijection, or there exists a one-to-one map, from the set to the set of natural numbers. Right? The set is uncountable if it's impossible to find such a one-to-one map. Okay, so you can classify the following sets in as countably or uncountably infinite. The set of integers, it's countable. What about Zn? Countable. Okay, so before that, so you said that Z is countable. What is the map? Yeah?
That is the natural.
No, Z, so this is natural number, right? So can you find a one-to-one map from the set of integers to the set of natural numbers?
0 gets mapped to 0.
Okay?
All the positive integers gets mapped to even numbers,
Okay?
and all the negative gets mapped to odd.
Right, so to be more precise, so the map would be, so f of n or f of x, in this case f of x is 2x if x is greater than or equal to 0, and it is 2x plus 1 if 2 times mod x plus 1 if x is less than minus 2x plus 1. You can verify that this is indeed a one-to-one map, and it accounts for all of the integers, right? Okay, so similarly you can define a map for Zn, right? Okay, so this is fine. What about the interval 0 to 1? It's uncountably infinite. What about the set of rational numbers? Okay, and how do you argue that this is countable?
We can map it to n square by saying that rational number has p divided by q form.
Can you again repeat? You can map it to?
We can first map it to n square. Like
Okay,
that is
sure.
Because we can tell it by b divided by q.
Sure.
N square means d square.
Z square, yeah.
Yeah, and d square is countable. So d square is mapped to b.
That's it, right? Any questions? Okay, everyone's convinced that Q is countable. Okay, so intervals are uncountable. The set of reals is uncountable. So therefore R to the n is uncountable, right? All right. So now let's define something called a metric. So given 2 points, we want to know how close these 2 points are, right? And depending on the problem at hand, you may want to have you may be using a different notion of distance or closeness between points, right? So a metric, so given any set X, right? It could be a subset of the reals, it could be a subset of Rn, it could be Rn itself, or it could be something very, very different, right? So given X, we say that D, a function D, which takes 2 elements from this particular set and outputs a real number, is a metric if it satisfies the following properties. So firstly, D of x1, x2, this is always greater than or equal to 0 for all points in X, and equal to 0 only if and only if x1 is equal to x2. So you take any 2 distinct points, then the metric should always give you a strictly positive number. If it's the same point, it should give you 0. Okay, it should be symmetric. So basically the distance between x1 from the distance required to go from x1 to x2 is the same as the distance required to go from x2 to x1, and it should satisfy triangle inequality. So d of x1 x2 plus d of x2 x3 should be greater than or equal to d of x1 x3. You take any 3 points, the shortest distance from x1 to x3 is always greater than or equal to the distance required to go from x1 to x2 and then x2 to x3. Right? So any such d is called a metric, or sometimes called a distance measure. Alright, so the standard Euclidean distance, you can verify that it satisfies all of these properties. Right? Yeah. Alright, so can you give some other examples of metrics? Okay, how do you define the Manhattan distance? What is a space?
Integers to real hard one.
Okay, so it's Manhattan distance between what? Between points. Okay. Okay, so basically your space is R, and d of x1 comma x2 is mod x1 minus x2. Right? This is a valid metric. Right? Okay. Any other examples? Yeah. Yeah. Any norm. Well, not the norm itself, but the norm of the difference between two vectors. Right? So you take say Rn, any x1 comma x2, so d of x1 x2 is basically the norm of x1 minus x2. It could be the 2 norm, it could be any general p norm. Right? Well, you could also define metrics on not just real numbers or subsets of real numbers. Right? Suppose I have the space of functions. Right? So my set X is, let us say, the set of all integrable functions, real functions on R. Right? The functions which are absolutely integrable. So I can say d of f1 comma f2 is integral minus infinity to plus infinity mod f1x minus f2x. Yeah. So this gives a notion of distance between functions. These are not points, but different functions. Correct? In fact, I can generalize this to a general p norm. I can just say this is raised to p raised to 1 by p. Right? So in many ways, I can treat function spaces like real valued vector spaces. Okay, any questions? All right. Fine. So now that we have all of this, let's try to understand what a closed set is and what an open set is, and some other properties which have geometric interpretations, but maybe you've not seen this before. So given any set, again, you can define it in a very general way, but we'll try to get the intuition and the interpretation for real spaces. So let's take any set X. Maybe you can think of it as Rn or R, equipped with some metric, right? So we say that a neighborhood of radius R around a point is basically the following set. So it's n R of X, which is basically the set of all points which are at most, which are strictly less than R away from this particular point, right? So for example, if you take real spaces, then it's basically, think of it as an open ball of radius R around the given point X. So that's what I call a neighborhood. It's also sometimes called an open neighborhood. Okay. So this is the definition of a neighborhood, but in general, I could define not just for Rn, but I could also define it for this particular space of functions, right? All of this makes sense. Okay, so if I take a set A, if A is some subset, then we say that X is an interior point of A, if I can find some neighborhood around A which is completely contained in this particular set. If I can find a neighborhood around X which is completely contained within the set A. So for example, if you just think of an interval, right? Let's take the interval A to B, right? What we want to distinguish is between points in the boundary of this set and points which are completely contained sort of inside the set, right? And as the term suggests, a point should be an interior point if there's some more room to go to the boundary, right? So it's an interior point if you can find some ball around X which is fully contained, or some neighborhood around X which is fully contained within the set. Right? For example, if I take maybe the closed interval A to B, then let's be more concrete, say the closed interval from 1 to 2, is the point 1 an interior point of this set? It is not. Why?
Making address back from, there's no room for.
Okay, yeah.
The left side is, we cannot find any number. I take just left of one would be serial will be outside the interval.
Correct. So let's see. So suppose I take the point 1. What does a neighborhood around 1 look like? Correct. So a neighborhood of radius epsilon is basically 1 minus epsilon comma 1. It's this interval 1 minus epsilon, the open interval 1 minus epsilon to 1 plus epsilon. And if I take the intersection with the set A 1 comma 2, it's not equal to this particular interval, right? It's not fully contained in the closed interval 1 comma, right? So therefore 1 is not an interior point. But suppose I take any point which is strictly greater than 1 but strictly less than 2. Is it an interior point? Okay. How do you prove this?
Limit epsilon to 0.
So just 1 second. So take any x which is greater than 1 but less than 2. Is x an interior point? Of the set 1 comma, that's what we want to answer. Okay, and the answer is yes, but why?
Epsilon 1 is 1, x minus 1 and epsilon 2 is 2 minus x. Take the minimum of those.
Okay, so again the intuition is that if I take any point which is strictly greater than 1 but less than 2, then there's always room on the left and always room on the right. Let's try to find out how much room I have to the left and how much room I have to the right. So let's take epsilon 1 to be x minus 1. I know that this is strictly greater than 0. Let me take epsilon 2, which is the room on the right hand side, which is 2 minus x. Again, I know that this is strictly greater than 0. Let me take epsilon to be the minimum of these two. Right? I know that there is this much space on both sides. I take any ball of radius less than epsilon. Let me take epsilon by 2. Right? So x minus epsilon by 2, x plus epsilon by 2. This interval is certainly contained within 1 comma. I can, well, it's, yeah, correct. I can take epsilon itself. That's fine. So anything less than or equal to epsilon is fine. Okay, so one thing what should be clear is that an interior point should always be a point within the set, right? That's important to note. Okay, so now neighborhood. Okay. So given a set A, the interior of the set of the set A is basically the set of all possible interior points of A. Right? Let me take the set again. Let's take the same set 1, 2. What is the set of all interior points of A? Open interval 1, 2. Does everyone agree? So the interior of 1, 2 is the open interval from 1, 2. Right? Okay. What about the open interval 1, 2? it's equal to the same set. Okay. Suppose I have a finite set. Right, just consisting of the points 1, 2, and 3. What is the interior of this set? Yeah. Why?
Double one. 1,
So you take this. So we're all viewing all of these as subsets of the reals, right? So I have 1, 2, and 3. These 3 points, right? Firstly, what is an interior point of any of these points? Right? So I take a ball of radius. Let's take the point 2. I take a ball of radius epsilon around 2. Is it fully contained in this set? So again, what is the neighborhood? So it is 2 minus epsilon, 2 plus epsilon. It is this interval, right? Is this contained in this set? 1, 2, 3? It is not, right? The interior can only be, or an interior point can only be one of these 3 points, correct? Is any of them an interior point? Is 1 an interior point? No? Does everyone agree that 1 is not an interior point? Okay. What about the point 2? Is it an interior point? No, it is not. The point 3? No. So none of these 3 points are interior points, right? So what is the interior equal to? It's the null set, right? So if you take any finite subset of real numbers, what is the interior going to be equal to? It is going to be empty, right? So now what if I take any countable set? What is the interior going to be equal to? It's still going to be empty, right? Because the open neighborhood, remember that the interior should be a subset of the set that it belongs to, right? And the open interval is an uncountable set, right? If I take a countable set and try to find the interior, it obviously is not going to be uncountable. Right? So the interior for any countable set is going to be empty. Right? So one final definition before we end this class. So a set is open basically if the interior is equal to the set itself. Every set is an interior point. Right? This is natural again for open intervals, but it also makes sense for more complicated spaces. For example, function spaces. So are finite sets open? Yeah? No, right? Because the interior of any finite set, in fact, any countable set is empty, and therefore every countable set, every countable subset of R, I should be more precise, every countable subset of R is cannot be open. Are open intervals always open? So what is the interior of any open interval? The interval itself, right? So it's open. What about closed intervals? What is the interior equal to? So the interior of a closed interval, this is the open interval a comma b. Is this equal to the set itself? So this is not open. Is a neighborhood open? It is open. Well, it could be for general. It need not be subset of R. All right. So let's stop here. Any questions? Yeah. Yes.
One mapping that I have is you map that but then prime numbers we do for the map. More elegant mapping.
Set of integers mod to n. You look at the set of integers modulo to n, right? So you go coordinate wise, right? In each coordinate number 1, it's mapped to, say, if the first coordinate is x1, then it is x1 times n. Second coordinate would be x2 times n plus 1. Coordinate number 3 would be x3 n plus 1, and so on. Will that be 1, 1? Okay, so let's maybe break it down into 2 dots. Let's move out, if that's okay.